Okay, so this is the third part of the lecture on Chapter 9, Gases. And in this part, we're going to see even more applications of the ideal gas equation PV equals nRT. And at first, we're going to see how to calculate density of gases using that equation. To really see this, what is the connection with the density, let's start with the equation PV equals nRT, and we divide this equation first by both sides of the equation by volume and then by RT. So effectively we are dividing both sides of the equation by VRT. So we're going on this side VRT, and then on this side also VRT. This is very much rearranging this equation for our purpose to see the connection with the density. So RT cancels with this RT, and on this side of the equation volume cancels nicely. So just for the convenience, this side of the equation, which remaining part is just number of moles divided by volume, I put it on this side of the equation when I'm writing here, and that this side of the equation is just P over RT. So now recall the definition of number of moles. The number of moles was just very much a mass of the substance divided by its molecular weight. So substituting now for the number of moles, just the mass divided by molecular weight, you can see this part here is just replacing the number of moles, which is formally anyway the definition of the number of moles. But in this case, you can now multiply this equation by molecular weight, and of course in that sense that the final equation which you see is this. Okay, so this is on the bottom. That's the final result of this rearrangement, where you have a mass of the substance divided by the volume of the gas, the mass of the substance which makes the gas, of course, its pressure, molecular weight of that substance divided by R, the gas constant, and the temperature of the gas. And if you recall the definition of the density from chapter 1, it was one of the first definition, numerical, sort of coming with the equation, where the ratio of mass over volume is just the density. So we just rearrange our equation, PV equals nRT, so we can see very much nothing else but the ratio of volume. So that's formally a density of the gas. So we can say that definitely density D equals M over V, and as we saw this in the previous slide, in case of when we apply the PV equals nRT, that connects to the property, the variables of the gas as pressure times molecular weight divided by RT. So this is very much equal to the density of the gas. So another way, you can say that knowing the pressure, temperature, and the molecular weight of the substance which is of the gas which we are really talking about, then we can determine the density of the gas. So that's how it is calculated. We can see in practice the example for calculating the density, and you can see this in practice. So for example, what is the density of carbon tetrachloride vapor at 714 torr, that's the pressure units, and 125 Celsius. So carbon tetrachloride, the formula is carbon CCl4, and if I calculate the molecular weight for it, is 154 grams per mole. Just remember that carbon is 12 grams per mole, chloride is 35.5, so times 4 gives me 142. Is it? Yes, I think yes. 142 plus 12. That's going to be 451 grams per mole. So this is very much based on the formula. Unfortunately, in the problem, you have a name, not the formula. So somehow knowing the nomenclature of these molecules, you could recognize that this naming is that formula, and then you calculate the molecular weight. We want to use the R constant as in the units of liters, atmospheres, moles over Kelvin, just because we kind of used to use it. So this is our maybe convenient choice. To be able to use this constant, we see that the pressure which is given to us is in unit of torr, not the atmosphere as the R constant value would suggest, and its units. So the next step is to prepare the pressure in units of atmosphere so we can numerically plug it into the equation. So 714 torr, we have to convert this to atmospheres, and we recognize that 1 atmosphere is equal to 760 torr. So torr cancels nicely, and numerically we can calculate in a calculator, and this is 0.939 atmospheres. The next is just very much plug it into the formula. So it's pressure, molecular weight, R value, and of course the temperature. 125 is in Celsius, so this is a wrong unit. Put this temperature unit in any kind of equation, especially in the gas law equation. So 125 plus 273 gives me 398 Kelvin. So that's very much the value. So the rest is just a numerical calculations which would lead to 4.43 grams per liter. That's the density of that carbon tetrachloride. What I really wanted to comment on is the cancellation of the units. So indeed, the unit you're supposed to see is grams per liter. So let's see. We convert the pressure to atmosphere to be able to cancel the units with the R constant. And of course, here mole cancels with mole, Kelvin with Kelvin. So you can see that the remaining unit is grams per liter. Okay, so this is very much what it is. So naturally, as you can see, the units come up from the numbers you apply. Now, down here you have another problem, as a practice problem, where the mean molar mass of the atmosphere in at the surface of Titan, Saturn's largest moon, is about that much. So the molecular weight, average molecular weight of the gas on a Titan is given to you. The temperature is given to you in kelvins already. Atmosphere pressure in atmosphere units 1.6. So the question is calculate the density. And you can see in here that all the variables which are given to you are already in the proper units to use the value of R of 0.0821 liters per mole. So this is the answer, and the calculation should be trivial, that the density is equal to the pressure, which is 1.6 atm, times the molecular weight of the gas, so this is 28.6 grams per mole, divided by 0.082. We can use even 0.6, it's a little bit more accurate value. This is the value from the table. And the units is liters, atmosphere, divided by mole, Kelvin, times the temperature, 95 Kelvin. So I want to show you again that that with that choice of R value, with these units, we're able to cancel atmospheres. We're able to cancel Kelvins, units of temperature. We're able to cancel mole here. And the remaining unit is, of course, grams per liter. So I didn't calculate this with a calculator at the very moment, but I believe that the number should be 5.9 or very close to it, and the unit is of course gram per liter. So that's very simple application of the equation, rearrange equation of the PV equals nRT to calculate the density of the gas. So notice that when we have that formula for the density, we can very much rearrange this equation very easily to calculate the molecular weight. Just in case if we can determine the density of the gas, or in the problem it might be given to us, but the question is asking about the molecular weight, we can easily rearrange this equation for the purpose of calculating molecular weight. So you can see that, I mean, to rearrange this, what you have to do is just very much multiply both equations by RT and divide it by P. This is for both equations. So you can see then you have, I mean, this is then RT over P, and then on this side of the equation, the P cancels nicely, R cancels, and T cancels. So you have very much that equation. Molecular weight equals dRT over P. Another way of describing the density, remember from the definition that it is just the mass over volume. So alternatively, if we do not have the density as given, like for example grams per liter or so, but instead we know the mass of the gas and its volume, that ratio is equivalent to the information on the density. So we can see applications of this equation to calculate the molecular weight. And here I'm giving you a simple example to see this in practice. Calculate the average molar mass of a dry air if it has a density of 1.17 grams per liter at 21 Celsius and 740.0 torr. So torr is pressure, temperature is in Celsius, density is also given. So here you have the answer, but here this time around I'm showing you how to solve it. So of course we want to use our beloved R constant, which has these familiar units of atmosphere over liter. So we have to prepare our given data for and convert for the proper units. So the pressure in torr has to be converted to atmospheres, which is very much using this ratio. Notice torrs are cancelled nicely, and the remaining unit is atmosphere. And then another thing which we have to watch out is the temperature, of course. So 21 plus 273 gives us the Kelvin value. This is specifically 294 Kelvin. And of course, we have that formula. Molecular mass is the density over RT times RT over pressure. We have the density 1.17. The R value is in units of atmosphere, liter, mole, and Kelvin. We have the temperature in kelvins and the pressure in atmosphere. And the reason why we need these in these specific units is to match with the value of R constant, its units. So we can, as you can see, very easily cancel the atmospheres. We can cancel liter unit as being on diagonal, Kelvin units for the temperature, and the remaining units, of course, grams per mole. So gram per mole, that's a molecular weight, and of course, molecular weight units. And numerically, I believe if you plug it in, it should be 29.1 or very close to it, grams per mole. This problem here is actually a repeat of the problem from the previous slide. So I think it's a typo that I have it here. So I'm not going to solve this problem again, but this one is, of course, giving you a molecular weight and asking for the density. So this slide is intended to introduce you to other examples of applications of the gas law equation, PV equals nRT, to relate this with the chemical reactions, and specifically chemical reactions which are involving a gas, either product or gas reactant. So in this example, we have a specific chemical reaction of a compound called sodium azide, NaN3, which composed to sodium and the nitrogen gas. And the problem stated is that and this is actually used in the airbags in the car, and the specific problem states that if the airbag has a volume of 36 liters and it fills up with the nitrogen gas to have a pressure of 1.15 atmospheres at the specific temperature, 26 Celsius. The question is, how many grams of the reactant in this reaction must be used to produce enough of the gas, nitrogen gas, to have this specific volume, this pressure at this temperature. So as you can see, you have all information needed to determine the number of moles of the nitrogen gas, because I mean, you can apply very much PV equals nRT. Rearranging this equation to calculate the number of moles would be just PV over RT. So gas data listed here in the problem is just volume, 36 liters. We have pressure 1.15 atmosphere, and we have, of course, temperature 26, but we have to be careful. This is Celsius, so we have to add 273, which is 299 Kelvin. This gas data allowed us to apply in this equation to calculate the number of moles of the nitrogen which we have to produce if it just which would satisfy these initial conditions. So plugging in this data, notice that atmospheres and liters, atmospheres for pressure and liters for the volume allows us to use that value for the R constant, which has the corresponding units, liters and atmospheres. In that way, atmospheres cancels, liters cancels, Kelvin cancels, and we have simply 1 over the inverse of the mole unit, which is of course mole. So numerically, if you plug it in the numbers like that, you should have 1.7 moles as information on the number of moles of the nitrogen. And from this point, when you already apply the gas information to determine the number of moles of the nitrogen, all the steps next are just very much steps which were introduced to you in chapter 4. So using the stoichiometric curve. So we're starting with information about the number of moles, which we just determined from the gas data. We use the stoichiometry of the reaction to convert information of the nitrogen, which is given, to the information of the reactant, which is here. Notice that the coefficients, which are of course important to determine this, is 3 and 2. So we have to convert this to the reactant, so we have stoichiometric coefficient 2 next to the NaN3, and next to the nitrogen it's a coefficient 3, so that gives us the ratio of 2/3. So when you multiply this by 1.7, gives you 1.1 moles of the reactant NaN3. And of course, to convert this, so this step would give us number of moles, and then to do this final step to grams, we have to calculate the molecular weight of the sodium azide. So we have molecular weight is 23 grams per mole for sodium, and we have 14 times 3 grams per mole for 3 nitrogens. So I think this should give us 65 grams per mole. So that's very much molecular weight. Number of moles times the molecular weight gives me the grams of the sodium azide. So that's very much a simple application of sort of gas information data and using it to the information about the specific chemical reaction. So here is another example, relatively simple, but this is example again where the gas information is used along with the information of the chemical reaction The chemical reaction stated in the problem is of course here and nicely already balanced, so you don't have to worry about that. And the question is, how many liters of ammonia, so this is that gas, at specific temperature and pressure are required to react with 1 mole of oxygen in this reaction. So the information is about, given information is about the other reactant. We know that we have 1 mole of oxygen in the problem, and of course the question about ammonia is very much how many liters of ammonia is very much required at the specific temperature and pressure. So the starting information is of course 1 mole of oxygen. Using the stoichiometric coefficient, we can relate the oxygen information to the ammonia information, and this is very much the ammonia stoichiometric coefficient is 4, the oxygen is 5. This gives us that specific ratio. Notice that its construction is so the oxygen information can be cancelled and replaced with ammonia information. So 1 times 4 over 5 gives you 0.8 moles of the ammonia. And of course, this is nothing else but the N in PV equals nRT. So if the question is asked about the volume of the gas, notice that now we have all information needed of the ammonia to calculate its volume. We just calculate the number of moles, the R value is given, and then we're going to have a choice of our familiar R value in units of atmosphere, liters, moles, and Kelvin. Temperature is given. The only thing, it has to be converted to the kelvins, and pressure is also given, and it's already in atmospheres. So here you have 0.8 moles of ammonia, which we just calculated based on the chemical reaction. The R constant in units of atmosphere, liter, mole, Kelvin. The 850 in Celsius plus 273 gives you 1123 kelvins. So here it is. And of course 5 atmosphere pressure. So you can see cancellation, mole, mole, Kelvin, Kelvin, atmospheres, atmospheres, and the remaining unit is liters. So the numerical value, when you calculate this in a calculator, gives you units of liters, and this is very much what I calculated, and the formal answer is 14.8. This is perhaps, when you're using the significant figures, you might very much get this number. Okay. Here I want to stay with the same problem, the same chemical reaction, but I'm going to change the question. So here it is. How many liters of all gases, and I underline all gases, which are products, are generated at 25 Celsius temperature, 1 atmosphere, if 34 grams of ammonia is used in this reaction? So all gases, and that's very more important, that means this as well as this. So 2 of them. And the information given to you is that I have 34 grams of ammonia. And all gases means that the nitrate oxide and water, both gas. So I start with the information given and apply this to calculate the number of moles, because if I'm not starting with number of moles, I cannot really apply that information directly to a chemical reaction using stoichiometric coefficients, but here it is. 34 grams of ammonia. I know that 1 mole of ammonia is 17 grams. I know that because 14 for 1 ammonia plus 3 times 1 for 3 hydrogens gives me 17 grams per mole. So that's what that number is coming from. And now I have to convert this to number of moles of all gases. So notice when it comes to all gases, I have 4, this is stoichiometric coefficient 4, which corresponds to 1 of the product, and then I have 6, which corresponds to the other gas product. So because it says all gases, I have to add the two together. Remember that in terms of the volume, all gases occupy the same volume with this, when it comes to the number of moles. So this is why I can simply add these two stoichiometric coefficients when the question is about all gases. So, and then of course this is converting information of all gases on the product side to information about the ammonia, which is given to you. So the coefficient next to ammonia is 4. So let me maybe use another. So this is 4, and this is very much this 4. And this 4 and 6 gives me this and that, and I have to very much add these two numbers together. So effectively I have like 10 over 4 when it comes to the mole ratios of all gases to mole ratios of ammonia on the reactant side. So if I do this, I mean, we can see cancellation of units if you want. This is grams, grams, ammonia, ammonia, and then you can say that that this is moles of all gases, both NO and H2O. So this is altogether 5 moles of gases. Okay, and then of course the volume, then we're going to apply the PV equals nRT rearranged to calculate the volume. So we have 5 moles of all gases which are produced. We have a corresponding R value, which indicates that we're going to use atmospheres for pressure, and the number is going to be calculated in liters. 298 is the corresponding temperature in kelvins. 1 atmosphere is here, and 5 moles we just calculated. So it's that's very much numerically, you should see a number like 122.27 liters. But in terms of units, you can see moles cancels with moles, atmosphere cancels with atmosphere, Kelvin cancels with Kelvin. So you're calculating this in liters. So let me introduce to another law, Dalton's law of partial pressure. So first of all, let's talk about what the partial pressure is, just in case if the given gas is a mixture of different compounds. Very much like in the previous slide, we just solved the problem where we calculated the total volume of the gas, which is made of the 2 compounds. So in principle, you are dealing with not just a pure compound, no pure gas, which is just 1 compound. In principle, you're dealing with some mixtures of gases. For example, air is a mixture of nitrogen and oxygen. So of course there is some kind of partial pressure which you feel because of the presence of the nitrogen in the air, and some partial pressure which corresponds to oxygen in the air. The two partial pressures of the oxygen and nitrogen is when you add the two, it's just total pressure of the air. Of course, there are some other gas molecules like carbon dioxide and others compositions which are relatively small. So the contribution of these molecules I'm going to assume as negligible, to be negligible. So in principle, when you're dealing with a gas mixture, you can talk about partial pressures of each chemical composition of that total pressure. So of course the graph here, a simple picture of the blue and red molecules demonstrate the addition of the partial pressures to make the total pressure. But in general, if you have more than just two mixtures, you can have as many compounds as you wish, but each compound will have its own partial pressure, which makes the total. So if you really want to talk about the partial pressures of each compound in the mixture, you can determine this based on the composition to make the total pressure. So how this is possible to calculate these partial pressures, we're going just to learn now. This is just only a formal definition of the partial pressure as belonging to a specific compound in the mixture of gases. Okay, so this slide, which introduces the Dalton's law of partial pressures and introducing formally the molar fraction as something convenient to define to calculate partial pressures. Yes, the slide looks a little bit busy with equations, and it might be scary, but hopefully it will be explained and it won't be as scary. So starting from the total definition of the total pressure as the sum of individual components, so-called partial pressures of the individual compounds in the gas mixture, where each of these partial pressure can be formally calculated knowing the number of moles of individual compounds like N1, N2, and 3, and of course the temperature of the gas mixture and the total volume of the gas mixture. So partial pressures, of course, can be calculated this way. Notice that if I, instead of writing this P1 here, P2, P3, I'm going to substitute these three equations for this P1, P3, P2, then I can very much write equations like that for individual partial pressure, which depends now formally on the gas data, such as temperature, volume, and the number of individual compounds in the mixture. And in that way, I can, as a sum of all this, I can calculate total pressure. If you examine this sum, you should notice that the value, the constant value R, the temperature, and the total volume of the gas mixture is common for all components of the partial pressures P1, P2, P3. So as the common factor, I can pull it out before the bracket, and simply you can see now that the total pressure is just the sum of the number of moles of individual components of that gas mixture times, of course, RT over V as corresponding to the rearranged equation of PV equals nRT. Where, of course, individual number of compounds is summed up to get the total pressure. Notice that if I define something which is called molar fraction, formal definition would be the number of moles of a compound, one of the compound in the mixture, divided by the total, the sum of all moles of the compounds in the mixture. This ratio is called molar fraction, and formally you can see that that this is actually equal the same as partial pressure of a compound to the total pressure. So if you do that, then you could have you can calculate partial pressures of individual compound 1, 2, and 3, knowing the total pressure of the gas mixture and its molar fractions. So specifically, kind of to get a little bit of a better idea of how this works, let's say that we have a gas mixture where I have, let's say, 5 moles of oxygen, O2 gas. We have 2 moles of nitrogen, and let's say we have 3 moles of carbon dioxide. So we have 3 compounds in the gas mixture with this specific amounts of the individual compounds. And molar fraction of oxygen in that mixture would be, of course, the number of moles of oxygen, which is 5, divided by the total sum. So it's 5 plus 2, 5 plus 2 plus 3. So this is 5 over 10. So, so molar fraction of oxygen can be calculated like a half. Now we can notice that we can calculate also the molar fraction of N2. In this case is 2 moles of N2 divided by 10, the total number of moles in the mixture, which is 0.2. And finally, carbon dioxide molar fraction would be 3 divided by 10, which is 0.3. Notice that if you sum up all molar fractions of all compounds in the mixture, the sum of all is always equal to 1. So, and also this allows us to, if we know, let's say that this gas mixture has a total pressure of, let's say, 5 atmospheres, then we can calculate partial pressure of oxygen in that mixture as molar fraction, which is 0.5 in this example, times 5 atmospheres. So so partial pressure of oxygen would be 2.5. And then partial pressure of nitrogen, of course, 2.5 atmospheres. Nitrogen would be 0.2 times 5 atmospheres. So this would be just 1 atmosphere coming from the nitrogen, and partial pressure of carbon dioxide is equal to 0.3 times 5 atmospheres. So this is 1.5 atm. So notice that if I indeed sum all the partial pressures of this compound, of that gas mixture, 2.5 plus 1 plus 1.5 gives you indeed the total pressure of the gas mixture. So in that sense, molar fraction is very useful in its definition to calculate uh, either partial pressures, knowing the total pressure, or as you can see later, if we know the temperature and the volume, you can also calculate the partial pressures using the standard equation, which is derived from the PV equals nRT. Let me have some numerical examples of that, more clean versions, which is on the next slide. Okay, so this is an example where we're going to calculate the partial pressures as well as total pressure of the gas mixture. And in this particular example, a gas mixture is made of the 6 grams of oxygen and 9 grams of methane. And so the composition of the gas mixture is known. The only thing is that the information is given in grams. So we have to convert this to moles. We also have the volume of the gas mixture being 15 liters. We have the temperature in Celsius, 0 Celsius. So it has to be converted right away. 0 Celsius plus 273. That's 273 Kelvin, which is important to when we are applying the equations. And of course, we're going to calculate the partial pressure of each gas, oxygen and methane, in the gas mixture, as well as the total pressure in that vessel. So we're starting by converting the mass information of each of the compound in the gas mixture. For oxygen, it's 6 grams divided by 32 grams, which is 1 mole, the weight of 1 mole of O2. 16 times 2 is 32. So the result is that we have 0.188 moles of oxygen. The same way we convert the grams of methane to the moles of methane, using the molecular weight of methane being 16 grams per mole, and gives us the number for moles. But then, of course, the partial pressure of the oxygen is going to be nothing else but the number of moles of oxygen times the RT over V. This is directly coming from the PV equals nRT, where we rearrange this to calculate P. And of course, if we're interested in a P of oxygen, the number of moles has to be number of oxygens. So here it is, number of moles of oxygen. Then we have the R constant, which has the units which we're going to apply our volume, and then we calculate the pressure. I'm going to show you this later, how it cancels, as always, in terms of units. And of course, temperature 273 kelvins. So in terms of units cancellations, mole cancels with mole, kelvins with kelvin, then liter cancels with liters, so the remaining unit is atmosphere, and then numerical value which you get in the calculator by plugging the numbers into this equation and calculating correctly is in units of atmospheres. Very similar way, you do the same thing for methane, but this time around you have the number of moles of methane and calculating partial pressure of methane in a gas mixture. So the only difference here is that number of moles of methane, and all the rest, which is characteristic of the gas mixture as its temperature and the total volume, is unchanged from the case when we calculated the oxygen. So the unit cancellations with the appropriate R value is exactly the same. So we're calculating this number in atmospheres. Of course, the total pressure is then just the simple sum of the two partial pressures of the two compounds in the mixture. So adding these two values notice they are anyway the same units, so it's not a problem of converting one to another. And so you have, or one to another, meaning that you usually, when you add the numbers which have the physical units, you really have to make sure that they have a corresponding units. So in this case, of course, it's atmospheres and atmospheres. That means that this is corresponding unit. That's the same unit. So that's very much what I wanted to comment on. So that's very simple application of the sort of variation of PV equals nRT to calculate partial pressure. Here you have another sort of exercise example, which is very similar in that sense that it's asking to calculate the total pressure of the mixture, which is composed of 2 grams of hydrogen and 8 grams of nitrogen at the given temperature and volume. So to solve this, you really have to start with converting 2 grams of hydrogen to moles of hydrogen, 8 grams of nitrogen to moles of nitrogen, and then applying very much the same strategy. The only difference is that now you have 10 liters for the volume. The temperature actually is the same, it's just given in kelvins. And if you use the R constant as is in these examples, you're going to calculate partial pressures of hydrogen and nitrogen, and then summing it up, you should get the answer as is given here. So I'm just lining out the problem, but I didn't really show it to you. Make sure that you actually solve that problem as an exercise. Okay, so in this slide, I wanted to give you an example of a problem which relates mole fractions to partial pressures calculations. And a problem states a study of the effects of certain gases on the plant growth requires a synthetic atmosphere composed of 1.5 mole % of carbon dioxide, 18 mole % of oxygen, and 80.45 mole % of argon. You really have to be careful here with what that statement mole % means, and of course it means that this is a percent fraction of the mole composition. Notice that if I add 1.5 for the carbon dioxide and 18.0 for oxygen and 80.5 for argon, this sums up to exactly 100, which is a scale for the percent. If I divide all these numbers by 100, so I will have 0.015 for the carbon dioxide, and I will have 0.18 for the oxygen, and finally 0.805 for the argon, the sum is going to be 1. So these numbers are nothing else but what we call mole fractions of these molecules in the gas mixture, making that synthetic atmosphere. So concentrating on a question in the part A is asking you to calculate the partial pressure of oxygen in a gas mixture if the total pressure of the atmosphere is 745 torr. So we can directly apply the formula that the partial pressure of oxygen in the mixture is simply molar fraction of oxygen times the total pressure. And when you look at this line here, this is very much what is calculated, 0.18. That's, of course, this number for oxygen, which is given in a problem. And the total pressure is given in the torr units. So, of course, if you multiply the two numbers numerically, your units for pressure is going to be still the same, torr. So 134 is the result for the partial pressure of oxygen. If you somehow want to change this to atmosphere, of course you can convert the units of 134 torr, and knowing that 760 torr is equivalent to 1 atmosphere, you can easily calculate that the partial pressure in units of atmosphere is 0.178 for that oxygen. Now going to the B part, if it says if the atmosphere is be held in the 121 liter space, so this is the volume of the gas at the specific temperature, how many moles of oxygen are needed? So in addition, we still have the same volume, and the partial pressure of the oxygen is not changed, as this is defining the synthetic atmosphere, and of course and it's related to the composition of that synthetic atmosphere. So what the problem is really asking is to find the number of moles of oxygen if you have that temperature, if you have that value of the atmosphere. So of course we can use PV equals nRT, where this is the temperature of the gas, the volume of the gas. This pressure, if this is pressure O2, then this is going to correspond to the N2. So converting this equation to calculate the number of moles of the oxygen, that's very much what it gives us. So remember, the partial pressure was already of oxygen was calculated here in torr and here in atmosphere. So because we want to use our familiar R units with the value with the units of liter and atmosphere for volume and pressure, we use the number for partial pressure in atmosphere. So here it is, which corresponds to applying it to this equation. Then for volume we have 121. And of course the temperature is 295, which is of course given in the problem. So unit cancellations is giving us Kelvin. Mole is not being cancelled, so I was just a little bit too quick here. Then another thing which is definitely cancelling is liter and liter, and finally atmosphere and atmosphere here. So you can see that you have inverse of the mole unit, so that that is the calculated unit, the moles, and the numerical value for the mole here, if you apply this within the calculator. So this is very much what it is. You can see that we use the molar fraction to calculate the partial pressure, and then we use partial pressure to calculate specific number of moles of oxygen which is required to fill up a specific space of that atmosphere. So this is it. Here you have yet another question relating the calculations of the partial pressure based on the molar fractions. And here we have the total pressure of the surface of the Titan is 1220 torr in units of torr, and then this atmosphere of that moon, on Saturn's moon, is made of 82 mole percent of nitrogen, 12 mole percent of argon, 6 mole percent of methane. So we already got familiar with this statement mole percent. So automatically we know that when it comes to molar fraction of nitrogen, it's going to be equivalent to 0.82. For argon, this is 0.12, and finally for the methane, that's 0.06. So the problem is giving us the information about partial molar fractions, and it's asking us to calculate partial pressure of each of these gases in that Titan's atmosphere. So, of course, the solution is lined out here. We're going to, of course, relate the partial pressures of each compound to its molar fraction and the total pressure. Total pressure is, of course, 1220 torr, and simply taking 0.28 for the nitrogen multiplied by total pressure gives you this number, and very much corresponding numbers, very easy for the argon and methane. And of course, that corresponds to the answers here. Notice the units of torr remains. I didn't really convert this just because that total pressure is given in torr units. So this is torr units, torr. And because of that, we have torr. As a practice, you can actually convert this to atmospheres unit if you want. Okay, so when it comes to partial pressures, I just also wanted to mention something which is related to the experiment which you did in the lab, and is when you were determining the R constant from the information of the gas which you collected through the chemical reaction. But if you recall, you collected this hydrogen gas above the water, and because of that, the gas which you collected had the two components: water coming from the liquid, and of course the hydrogen gas which was produced by the chemical reaction. So in that sense, you had two the gas is made of the two compositions, water and hydrogen. To determine only the part which belongs to hydrogen, you had to subtract the partial pressure of water, which is of course, the value is dependent on the temperature of the of the water. So that was given in a table. So just to understand of what was going on and why you had to subtract this is just because you wanted to have information only about the hydrogen gas in that mixture. So remember, this is somehow connected of what we learned by recognizing that the total pressure is very much in that mixture was the pressure of the hydrogen gas plus water. So So then the pressure of the hydrogen, which was applied to the equation, and the number of moles of hydrogen was obtained from the chemical reaction. You definitely, are rearranging this equation where you have to sum up all the compositions of the partial pressures to get to the total pressure. If you have two compounds, water and hydrogen gas, then the total pressure, which was atmospheric pressure, minus the water partial pressure, gives you the pressure of the H2 gas. So that's somehow how this connects with whatever you did in the lab to determine the pressure of the hydrogen gas after the chemical reaction was completed. Okay, so as we're closing already the chapter on gases, chapter 9, it is very important to get familiar with some of the concepts associated with the modeling of the gas. So the kinetic molecular theory is the model which helps to understand the behavior of gases, and here in this model we vision the molecules of the gas state as simply a large collection of molecules which are in constant motion, and they are simply either bumping to each other or bumping over the walls of the vessel then contain, and of course they, in that way they occupy all space. What is also important is that they do not interact, they don't have any attraction or repulsive forces between the gas molecules. So in that way they just have some kind of kinetic energy, and the molecules move with some kind of speed, and the theory tells you of how that kinetic energy of molecules relates to the variables which we use to describe the gas as temperature, pressure, and volume. One important aspect of the kinetic molecular theory is to understand that the average kinetic energy of the molecules which are in constant motion in a gas phase is going to be proportional to the temperature. So this is very much important statement. The average kinetic energy of molecules is proportional to the absolute temperature. And of course, you have on this graph here, you have a count of number of molecules which have a specific velocity, which is shown here on the x-axis. And you can have, sort of the graph shows you a distribution of these molecules at certain temperature. This is of course specifically for oxygen, but general shape, sort of this bell shape of the distribution of the velocity is characteristic. And of course, on average, this is very much this sort of average. This is of course the highest possible velocity, so molecules with which have the most probable velocity, but on average, the average is a little bit lower than this number, just because if you notice the bell shape is not symmetrical. It has a little bit of a tail on the higher velocity. So this is maybe not as important how this shape looks like. It's just showing the distribution of molecules with a certain speed. And of course, this around this point is the equivalent speed to so-called average kinetic energy. And this kinetic energy is very much proportional to the temperature. Also meaning that when the temperature is constant, and this is very important, when the temperature of a gas remains constant, the kinetic energy is not changing. Okay, so it's a constant at a specific temperature. The moment when the temperature rises, it's increasing. When the temperature is lowering, the kinetic energy decreases. Okay, so this slide actually gives you a graphical example of how the average kinetic energy is proportional to the temperature, and you can actually have a formula for it. So here is formal sort of little derivation of how velocity depends on the temperature, or kinetic energy depends on the temperature of the gas in this formulation of a kinetic molecular theory. So first of all, the thermal kinetic energy associated with the temperature is equivalent to 3/2 of RT value, where this is the temperature and R is a gas constant. And of course, in physics, the kinetic energy formula is just 1/2 of mass times the velocity. So putting these two formulas together as very much, they are equivalent, because this formula tells you about kinetic energy as a function of temperature, which comes directly from the kinetic molecular theory, and this one is from physics. So in that way, putting it together like this equation allows you to calculate velocity of molecules at a given temperature and a given mass of the molecules in a gas phase. Notice that we have, of course, the square value here. So specifically, if we take the square root of 3 times RT divided by m, we are able to calculate the velocity of the gas. If you recall the previous slide, the average velocity associated with the average kinetic energy was on a bell shape around here. This is a bell shape for 100 kelvins. If you rise the temperature, this is more or less here, 500 here, and 1,000 around here. It's a slightly on the right-hand side from the maximum value. So these are these values for the velocity. Remember that this axis has the velocity. So this is why I'm sort of pointing out the velocities which would be calculated according to this formula. But the general shape shows you that if this is specifically for the nitrogen gas, so with a specific molecular weight, so the mass is constant. So you can see that as the temperature is rising, from 100 to 200, 500, and 1,000 kelvins, the average molecular velocity is also rising. Another very important prediction which comes from the kinetic molecular theory is about the velocity of the molecules in a gas phase should be inversely proportional to their mass at the constant temperature. And this is very much what the theory predicts, looking at the equation. But here you have actually experimental measurements of this molecular speeds distribution in the form of these bell shapes, taken at the constant temperature, 300 kelvins, and 3 different bell shapes which you see here are taken for the 3 different gases, chloride being the heaviest, nitrogen, which has a middle mass, and then the lightest from the 3 is a helium gas, and of course these masses are of course, directly proportional to the molecular weights of these gases, of these elements. So you can see that, of course, the heavier compound, the heavier gas, will have a lower molecular speed than, and the lightest element of the three will have the highest average molecular speed. So this is very much showing you how these bell shapes are changing as a function of mass. Now, using that theory, we can easily calculate the so-called root mean square velocity of any molecule at a given temperature, as the velocity is proportional to the temperature. But in this case, and if you recall my first lecture on gases, I mentioned that you're kind of free to choose your R constant. But in this specific case, because you're calculating the velocity, you really have to use the R value equal to 8.314, which is in units of joule per mole per Kelvin, because you're calculating the energy. Of course, so the temperature should be in kelvins as always, and the mass in physics is always kilograms. So your molecular weight, which is usually grams per mole, you have to convert to kilograms per mole. In that way, the units which you're calculating for the velocity is going to correspond to meters per second. So these are the restrictions which you really have to do this equation to be able to calculate the numerical value which corresponds to meter per second. So in this particular case, we have the molecule carbon dioxide. So we're starting with calculating molecular weight of the carbon dioxide as always. This is 12 for carbon plus 2 times 16 for oxygen gives you 44 grams per mole. But you really have to convert these grams to kilograms. So the easy conversion is just to divide this by 1,000. So this is why you have this this number as a conversion. Of course, 25 Celsius you have to convert to kelvins, which gives you 298 kelvins. And then, of course, the rest is just to apply this to this equation. You have, and of course, the R value has to have the joules in it. So this is the only place where you have to be specific which R value to use. And you have Kelvin, cancellation, mole and mole, and then you have joule per kilogram. But that if you recall, joule, that's energy, and you have kinetic energy m v squared. So if this is joules, okay, units of joules, and this is kilogram, then of course this is meter over second squared. And of course there's a factor half, but that doesn't have a unit. So now you can see here joules per kilogram. So joules per kilogram would be nothing else but meter over second squared. So taking the square root of it gives you units of meter per second. And the numerical value, when you calculate and taking the square root, is 411 meters per second. So these molecules are really moving very, very fast. These slides introduce you to the concept of spreading one substance through a space or throughout a second substance uniformly, very much like a perfume in a room. That process has a name, and it's called diffusion. So it's just based on the fact associated with the kinetic molecular theory that the molecules are very much in constant motion. In that way, after some time, it will fill up the entire space. So the example of perfumes I gave you as a spreading in gas state. But the diffusion examples you can also have in a liquid state, and here in this little picture you have sort of a picture of the diffusion in process. At the end of the diffusion, of course, you can expect that this smoky blue distribution of molecules going eventually to create this uniform blue color in a volumetric flask, and this is not volumetric flask, in the Altmaier flask. So that's just very much an example of a diffusion. Another name associated with behavior of gases is the name of effusion. So effusion is very much an escape of a molecular gas through a tiny holes of if there is a hole in the wall, then of course the gas is going to escape, and the process is called effusion. And of course, because the lighter elements are expected to have higher molecular speeds at the given temperature, the balloon filled up with a lighter element like helium will escape from the balloon much quicker than, let's say, the balloon which fills with the air, like mainly nitrogen gas. Finally, let me introduce you to the Graham's law, which is directly related to the kinetic molecular theory, which of course said that the kinetic energy is very much equal to the thermal energy, which is very much dependent on the temperature. So also it means that if you're comparing the average kinetic energies of the two different gases with different masses at the constant temperature, the same temperature, then they have to be equal. So to give you a little bit of an imagination of what it could be, let's say that M1 corresponds to a nitrogen gas, and M2 corresponds to something light like helium gas. So of course this one has molecular weight about 28 grams per mole, and this one has 4 grams per mole about. So this one is heavier, this one is lighter. So when it comes to the molecular speed, this one is going to be slower, and this one will be faster at the same temperature. But when it comes to the average kinetic energy at the given temperature, the energy is the same. Okay, so it's equal. So you can express this here in terms of the formula for the kinetic energy, mass times velocity squared. And of course, now this is for the nitrogen and velocity of the nitrogen, and the mass for helium, velocity of the helium. Notice that this is equal because the heavier molecule will move with a slower speed, but the lighter element will move with the higher speed. And of course, this balance out. Heavier mass, lower speed, lighter mass, higher speed. So get rid of the factor 1/2, you can have very much relationship between these velocities and masses of the two different gases, very much like that. And from that, putting the masses ratio on one side and velocities on the other, you can have this equation. And if you're interested to find the relative speed of the two molecules, depending on the mass, then you can just very much take the square root of the mass ratio must be equal to the velocity ratio. And notice that, of course, the ratio is inverted. So this is 1, velocity 1 is on the bottom here, and the velocity 2 is on the top, but in the mass ratio, velocity is on the bottom of the ratio. So so this is very much this formula in the red box. And I'm going to I'm going to erase all that so you can have a clear vision of what that formula is. This is the Graham's law. And I'm going to give you one more example to demonstrate this, this relationship. So here's an example of the problem which will use the Graham's law to solve the problem. The unknown gas composed of homonuclear diatomic molecule effuses. Just wanted to recall that effusion means the escape of the gas through the hole in the container. Effuses at the rate that is only 0.355 times that of oxygen gas at the same temperature. Calculate the molecular mass of the unknown gas and identify it. So it looks like we have information about the unknown diatomic molecule in terms of the speed in which it moves compared to the oxygen. So we can write something like that the velocity of a movement of the molecule X, unknown, compared to the velocity of the oxygen is equal to 0.355. But Graham's law tells us that that ratio is also equal to the square root of the molecular mass of oxygen divided by the molecular mass of the compound X. And that, as you can see, allows us to solve for the molecular mass of the compound X. Of course, molecular mass of oxygen, we use molecular weight. And so this is 16 times 2, that's 32 grams per mole. So we have 0.355 equals to 32 grams per mole divided 32 divided by the m of x, which is of course a mass of the unknown. So another way we can say that it's 0.355 squared must be equal to 32 grams per mole divided by m of x. So that means that m of x must be equal to 32 grams per mole divided by 0.355 squared. And that is equal to 254, and the unit is still there, grams per mole. Notice that this ratio doesn't come with any units because whatever the velocity units were, they were cancelled out. So this is the molecular weight of the unknown gas. But in addition, we have to identify what kind of element is this. So it looks like it's diatomic molecule, so it looks like it's X2, whatever the X is, as the symbol of the element. So that means that the mass of the individual atom X must be 254 divided by 2, which gives me 127 grams per mole. If I go to the periodic table, I identify this as iodide, a symbol I. And of course, if I have a diatomic molecule, that is going to be I2. And the molecular mass of I2 is indeed 2 times 127, which is 254 as we calculated. So this is very much a simple solution. You can see that when you're reading the problem for the first time, it sounds like maybe it's much more complicated than actually it is. And it's a simple usage of the Graham's law. So this is the very last slide on the chapter 9, and this is just only mentioning that the ideal gas equation, which is of course PV equals nRT, is the equation which really nicely works for most of the gases, but this equation comes with a specific condition that the molecules in the gas are not really interacting. There are no any forces between them. So there's no attraction, there's no repulsion. In a real gas, you might have attraction or repulsion forces. And in this specific example here, for the real gas, you can see sort of the arrows shows the attraction forces. And because of that, it reduces the overall space, the volume, compared to the ideal gas. So simply because the molecules are attracting each other, overall volume is reduced. So this is very much due to these interactions, a slight deviation from the ideal gas picture. Also, when it comes to the pressure, the ideal gas, when the molecule of the ideal gas will impact the wall, which of course generates the pressure, something which we measure the pressure by. So it's a force on the specific area. If you have the real gas and some molecular attractions are present, that overall force of that molecule, which would generate the pressure on the wall, is of course reduced because it doesn't have as much force to impact the wall. And of course, there are some corrections to that ideal behavior described by PV equals nRT. And one of the correction, which of course counts for these attraction forces, is so-called van der Waals equation. And the van der Waals gives you a correction for the molecular attraction in the pressure part and the volume part. You can definitely see if these corrections are zero, then this equation would be P times V equals nRT. But the van der Waals counts for these corrections, and that's very much what it is. I will not be asking you on the exam for that van der Waals equation. I just wanted you to be introduced to this equation and understand that the ideal gas equation PV equals nRT is of course the ideal gas equation, which works for most of the gases. But if you really want to study the differences between particular gases in details, you would have to use equations such as the van der Waals equation to study these differences in details.